Hello, students. This is Dr. Stover, and welcome to distance learning. Um, Again, I know you guys probably aren't very happy about it. In reality, I'm not happy about it either, but it is what it is. Okay, so we're just going to truck on through. I have already posted a discussion for today's lecture, which will be distributed over multiple videos. So remember that when this one ends, that's not it. You have multiple videos to watch because the school specifically asked us to consider your internet requirements and to not have super long videos. So there will be no video that's over 15 minutes. So that means that we have to have multiple videos. All right, but we're going to pick up where we left off in class last time. So where we left off last time was we talked about first order reactions, we talked about second order reactions, and we talked a little bit about lab, but I had to shoot past half-life. So I want to talk about half-life a little bit more in detail. I will talk about lab again, okay, if you have questions on that. But all right, so half-life. Half-life is exactly what it says. Half-life is how long it takes for half of a reactant to react. So what is the lifetime associated with half of something going away? So if you started with a concentration of 1, as in the picture, according to this timeline, it would take 100 seconds to get to 0.5, which is half of 1. It would take 100 more seconds to get to half of that, which would be 0.25. If we do a third half-life, that would be half of 0.25, which would be 0.125, and that would be at 300 seconds. Okay? And for a first order reaction, half-life is constant and independent of concentration, and I'll show you that on the next slide. If you're interested about radioactive materials and nuclear chemistry, all radiation follows first order kinetics. So it's all independent of the concentration. So it makes it really easy for us to study. But let's now relate what we're talking about here, half-life, to these labels that we've used originally. So in our original equations, we said that the concentration of A after some given time, we represented as AT. Well, now we're saying we know what this is going to be. It's going to be half, so 0.5, half of the original concentration. So the easiest way for us to sort of consider this is to then distribute this idea into the previous equations that we talked about, right? And we like halfway because, yeah, it's just like the slide said, it's super convenient for talking about, ladies, sorry, cats are fighting. 1 second, I'm going to pause the video and I'll be right back. And I'm back. Sorry about that. Okay, all right, so half-life, super convenient. It's just an easy way to say if something is extremely reactive or not. Does it have a super long half-life? Does it have a super short half-life? Obviously, we are concerned about the things that decay on a very quick order than we are things that decay on a very long-term scale. Okay. All right. So now let's relate this, like I said, to the previous equations we've talked about. So we're going to start with first order. Okay. So this was our first order equation. Remember, you do not have to memorize this. This will be provided to you in any sort of quiz or exam. Okay. But this is our integrated first order equation. So now what we've done is we've substituted AT for half of A0. And then basically we can just do some algebra, okay? So the first sort of algebraic thing we can do is notice that A0 divided by A0, anything divided by itself, goes to 1, right? So it completely disappears. Also note, I didn't say this before, that we're specifying that T has a subscript of a half, specifically saying this is the half-life. That's what the 1/2 on the T is doing. It's just specifying we're talking about half-life. All right, well, if you take the natural log of a half, that's a constant value. The natural log of a half is negative 0.693. And so this is now equal to negative K times T times the half-life. So if you divide both sides by negative K, the negative goes away because negative divided by negative is positive. And we just get that the half-life is equal to 0.693 divided by K. Notice No initial concentration pops up in that equation at all. And this is what radioactive and nuclear chemistry follows, this equation right here. It is not dependent upon the initial concentration. Now, this equation you do need to have memorized, okay? I do expect you to have this one memorized. I do not expect you to have this one. So this one I will give you. I'm not going to give you this. Okay, so this one you should really know and have it memorized because it's a lot simpler of an equation. All right, what about for second order? Okay, here is our integrated equation for second order. Again, we're going to substitute T for T1/2, and we're going to substitute a half A0 for AT. Okay, again, we're just going to do some algebra. The first thing we can do is say 1 divided by a half is 2. Do some simplification here to get to here. And then we want to get our fractions on the same side. And since they have the same denominator, we can combine them. And so it's 2 minus 1 over A0, which is just 1 over A0, is equal to KT. So divide both sides by K, and we get our second equation. So the half-life in a second order reaction is equal to 1 divided by the rate constant, K, also divided by the initial concentration. So while first order is independent of the initial concentration, second order kinetics is not. Okay? Luckily for us, radioactive decay doesn't follow this. Otherwise, that would be a bigger thing to be concerned about. Okay, so let's take a look at our graph here. So here we have the reaction of butyl chloride with water, and it's a first order reaction, okay? Well, we know for sure, hopefully, by looking at this graph, you know it can't be zero order because this is time versus concentration, and it is not a straight line, okay? So you know it can't be zero order. So your only options at this point are first or second. I'm telling you it's first order, okay? So using the graph to the right, estimate the half-life for this reaction. Well, right off the bat, the first question you might want to ask yourself is, do you need to know if it's first or second order to answer this question? And the answer is no, not if you have a graph in front of you. You just want to know what the half-life is. So we're starting with 0.1. Half of 0.1 is 0.05. And I just need to follow around over here until I hit this line. And then approximate what that time is. So to me, that looks like 340. You may say 350, 360. Doesn't really matter. You're in the ballpark, right? So to answer the half-life, if you have a graph like this, you don't need to know the reaction order. However, if they ask you for the rate constant, that's when you have to know if it's first order or second order, because you got to know what equation to use. So you know it's first order. First order is 0.693 divided by K. That's what half-life is. But in this case, they're not asking for half-life, they're asking for K. And we've talked about these types of equations before, but remember that half-life and K are interchangeable as far as the math is concerned. So half-life is equal to 0.693 divided by K, or you could say K is equal to 0.693 divided by half-life. K and half-life are interchangeable in that equation. Okay? All right. So then if we want to know K, all we got to do is say 0.693 divided by the half-life. So 0.693 divided by 340 seconds. And if we do that, which I'm doing right now on my calculator, and hopefully you are as well, I get a very small number, right? So I get 2.0 times 10 to the negative 3. And then think about what your unit is going to be. 0.693, that's just a unitless integer, right? But you aren't just dividing by 340, you're dividing by 340 seconds. So your unit is an inverse second, okay? So 2.0 times 10 to the negative 3 inverse seconds is the correct answer here. Now, I showed you this at the end of class last time when we were talking about a little bit associated with the lab and everything. So if we look right here, this gives us our zero order, first order, and second order information. It gives you some example rate laws of each. Remember, another way to write this one would be rate equals K times the concentration of A times the concentration of B, right? Because 1 plus 1 equals 2. Okay, so this isn't the only way to do this. Okay, these are the units of those. Okay, you should be able to calculate these, but if you wanted to remember them, you could. These are the integrated rate laws. I don't expect you to do any math with this one. We didn't talk about this one in class. I do expect you to be able to do math with these two, but again, I told you you don't have to memorize them. These are some sample graphs of what they look like and what their slopes are equal to, right? So for second order, time versus inverse concentration, the slope is K. But for zero order, time versus concentration, and for first order, time versus natural log of concentration, the slope is negative K. But either way, the slope always gives you K. It's just either going to give you K directly, or it's going to give you the inverse of K, so the inverse of the rate constant, and then you would just have to multiply by -1 to figure out what K actually is. Okay, these are the half-life expressions. I told you that you need to memorize the one for first order and second order. Don't worry about zero order. I'm not going to ask you about it because honestly, zero order overall kinetics is some of the weirdest kinetics out there because you're looking at rates that don't depend upon concentration, which means they only depend upon temperature and things like that. We'll talk about temperature effects in just a minute, but we're not going to associate it to an equation. Well, we are, but not this equation, not this. We'll associate it to a different type of an equation called the Arrhenius equation. Okay? All right. Well, this is going to be the end of the first video because I feel like this is a good stopping off point. Remember, this is not your only video, so you need to click on the next link. Okay? All right. I'll see you in a few seconds.